Anthony is now claiming that atmospheric pressure does not exist, so I would have to assume he has never driven down a mountain road and wondered why his ears have popped. Now, this was on a recent presentation on Ranty Flat Earth channel. Now, as usual, Anthony cherry picks data to support his claim, and the underlying theme is there is no gravity and there must be a container above the earth. Now, the irony is that in the real world there is nothing that supports anything that he said. And he has an email exchange with the astrophysicist Danny Faulkner, who confronts him with this, and it goes right over Anthony's head. So let's listen to Anthony, and here are a couple of key points.
So gas pressure pushes out against the surface of the container in all directions evenly. That's Pascal's law. Now, it's pushing out in all directions evenly, right? Nathan says frequently that you can't have gas pressure in a container. The sky's not a vacuum, and he's right.
So yes, Anthony is correct about Pascal's law, and this applies to both a gas or a liquid. And here's a diagram showing how a hydraulic system works. But Pascal's law is not one sentence. If Anthony had done more than just cherry pick the sentence he wanted, he would understand that this law is for liquids and gases at rest, and neglects the weight of the gas or liquid. And Anthony also ignores that if we apply Pascal's law to the flat earth with a container, yes, we would have equal pressure on all sides of that container, but this means there would be no pressure gradient. So let's take a listen to Nathan as he explains the reason that he thinks there's a container. This is from a flat earth debate.
So we come along and go, well, what's the gas pressing on? And that is essentially the end of that argument. It can't press on a vacuum, it would disperse into it. So the necessary antecedent, the container, debunks the argument that the sky is a vacuum.
So this is the basis of Nathan's logic. If gas disperses into a vacuum, then the sky vacuum would suck the atmosphere up. And since we don't see the atmosphere getting sucked up into the sky, we now have the necessary antecedent of a container. And of course, this is a container that nobody has ever seen. Antecedent? No. Logical fallacy? Yes.
But they start with this definition that states that actually it's the weight of the atmosphere pushing down. And they indicate it with arrows. That's literally the opposing arguments. They can't redefine something and say it's the opposite just because it suits their model. That's complete horseshit. They've got to define it the way that it is, because gas pressure is pushing out in all directions. This nonsense that they've got on screen is completely the inverse, and it's only in their model where this applies. Because in real world, gas pressure doesn't do what they say it does. Gas pressure does what we can demonstrate that it does on a smaller scale in a lab, time and time again.
Again, another example of simplistic thinking. So where did he come up with this nonsense?
Gas pressure, we know that the pressure is the force that the gas exerts on the walls of its container. It's literally everywhere, this. You've got to have a container. That's our argument.
So again, Anthony uses one sentence to support his claim, and he ignores this, the very first sentence. Pressure is a force exerted by a substance, and a gas is a substance per unit area on another substance. Well, the surface of the earth is another substance. I mean, Anthony only understands this. He only understands that gas pressure inside a container pushes out. Well, Anthony, I have a question. In what direction is the atmosphere pushing on the outside of the container? Well, atmospheric pressure is pushing in on the container's outside. So yes, the atmosphere can also push on the surface of the earth. And we know that this pressure is the weight of the air column on a unit area. And we can measure this with a barometer We know there are slight fluctuations with different weather conditions, and we also know that when we go up in altitude, this pressure drops. Let's be honest, to really understand how these laws work, you have to have a really good understanding of math. Here's some of the math required for Pascal's law. Now, my brother had thermodynamics in university, and he said it was one of the most difficult courses that he took. And look at some of these formulas. And these guys are two proven math illiterates. I mean, here's two simple concepts that they couldn't even comprehend. Yet somehow they think they're experts in physics? So let's continue with Anthony. And again, here are some key points.
A couple of weeks back, I cited this. I made this video up, and what it shows is that this is gas pressure. It's coloured so that we can see it, and this is a vacuum. Doesn't matter how much of a vacuum; it's just lower pressure than this. There's a tap. It separates the two. When you open the tap, it fills the available volume. That's what the science tells us, and that's also what we can demonstrate on a smaller scale. The minute the tap's opened, it immediately fills it. It doesn't gradually do it. It doesn't peel off just the top layer of the gas pressure. All of it immediately goes.
So yes, this is a very good experiment that shows how gas pressure works in a container. But what Anthony says here is also very important. It doesn't matter how much of a vacuum, it's just lower pressure than this. Because we know that gas wants to move from a higher pressure to a lower pressure. But another important thing that Anthony did not mention is that at the end of this experiment, all of the containers have equal pressure. So let's apply this to a flat earth with a dome container. So here we have sea level atmospheric pressure, 14.7 psi with a barrier. At a higher altitude, we have lower pressure or a partial vacuum. And as Anthony says, it doesn't matter how much of a vacuum, it's just lower pressure than the 14.7. And if Anthony is correct, when the barrier is removed, it fills the vacuum. But of course, this means there would be equal pressure on all sides of the container, and therefore no pressure gradient. So if Anthony and Nathan are correct, we should see an atmosphere that has equal pressure at all altitudes, not a pressure gradient. And of course, in both cases, I have ignored weather systems where we have highs and lows, but these only vary by a few psi. So what do we see in the real world? Now I'm going to use this vacuum pressure chart. It goes from sea level, which would be a 0% vacuum, all the way to space with 100% vacuum. And there's a variety of different methods to measure pressure, but we're going to use PSI, which of course is 14.7 at sea level and 0 in space. And of course, in between, we have partial vacuums of varying strength, because as Anthony says, it doesn't matter how much of a vacuum, it's just lower pressure than the 14.7 psi. So let's take a look at Southwest Airlines Flight 1380. I'm sure most of you have heard of this. They had an uncontained engine failure at about 30,000 feet. Debris broke a window, causing a rapid depressurization of the aircraft. Unfortunately, a passenger was half pulled out of the window, and she later died from her injuries. But the pilots did make an emergency descent, and with their skill, they were able to land the aircraft. Now, at altitude, aircraft interiors are pressurized, but they're generally pressurized between 6,000 to 8,000 feet. So a cabin pressure at 7,000 feet would be 11.3 psi. That plane was flying at 30,000 feet, so the atmospheric pressure was 4.37 psi. So here's a cross-section of the fuselage showing both the interior and the exterior pressure. And of course, when that window blew, it was a rapid decompression. Now, if we go to that vacuum pressure chart, I have 4.41 psi here, which is just a little bit higher than the 4.37. So at 30,000 feet, there is about 70% of the vacuum of space. So this pressure differential caused a rapid decompression of that aircraft. So the question for Anthony and Nathan is, why isn't this 11.3 psi at 7,000 feet in the mountains being sucked into the lower 4.37 psi at 30,000 feet? This is a 70% vacuum, and you saw what happened in that aircraft. And of course, the sea level atmospheric pressure certainly isn't getting sucked up into the 70% vacuum. So where is your container that stops this? So here is another example. This is the Red Bull Stratos jump at 127,725 feet. So Felix Baumgartner at this point is depressurizing his capsule so he can make the jump. And look at the atmospheric pressure, 0.07 psi. This is 99.5% of the vacuum of space. So again, why isn't the atmosphere at sea level getting sucked up into that almost non-existent pressure at 127,000 feet? Are you going to claim that 99.5% of the space vacuum isn't quite strong enough and you need that extra 0.5%? So where is that necessary antecedent, the container that is stopping this? So Anthony recently went on the Flat Earth debate, and he had an email exchange with the astrophysicist Danny Faulkner about this very subject.
He said, but there is no container between Earth's surface at 120,000 feet above us. Therefore, if what you are claiming about the air around us is true, then the air at ground ought to be sucked up into the vacuum at 120,000 feet. The fact that it doesn't ought to tell you that there is something very wrong with what you are claiming.
Yes, Anthony, Danny Faulkner is correct. You are claiming that this is not possible, but this is reality. And there is no container. Where is the container at?
Stop.
Now I'm like,
Hold on. That's
wow.
circular reasoning. That's pointing at the sky and saying, because I believe the sky is a vacuum, and it's not dispersing into my fundamentalist religious belief in a sky vacuum, well, then there's something very wrong with what you're claiming. No.
Yeah.
His first statement is our claim. Again, it's
Yeah.
somebody else that's decided to reassert our own statement back to us like that's some sort of defence. Yeah, that's correct. We wouldn't have any gas pressure, Danny Faulkner. If the sky was a vacuum, correct. All of the gas we're breathing here at ground level would fuck off into the sky vacuum, as you correctly assert. The fact that you believe it's a sky vacuum isn't a defence. That's circular reasoning. For the love of God.
Reality check, Nathan. There is a vacuum at 127,725 feet. And this is 99.5% of the vacuum of space. And Felix's capsule did not go through a container. Your container is just a fantasy that only exists in your head. I mean, this is the fundamentalist belief of a zealot. Let's be honest, this is an ignorant concept for ignorant minds who ignore the reality of the world around them. So the flat earth mantra that gas pressure can't exist next to a vacuum, therefore there must be a container, is 100% bullshit. You have absolutely no evidence of this fantasy container, but the Red Bull jump showed that there is a vacuum at the edge of space. So why do we have an atmospheric pressure gradient? Because we live on a globe and gravity is a reality. Time for you guys to wake up and smell the coffee.